So an and a dagger n are eigenstates of H with eigenvalues En minus h bar omega and En plus h bar omega respectively. And both the things on ket n can generate new eigenstates which will lower and higher by 1 unit of h bar omega. 1 unit of h bar omega. The lowering operator ASI will have the energy eigenvalue En minus h bar omega, and raising operator, the Hermitian conjugate, that will give you A dagger psi will give the eigenenergy value En plus h bar omega. So they are called ladder operators. Okay. And the graph, this is the harmonic potential. We said already, this is about harmonic potential. So half kx square. When x is a positive value, we will get this. When x is a negative value, this is x squared is there. Okay, so again this will become plus value. So that's why it's termed as exactly harmonic potential. Okay, and the energy will be for the first one, En, we are going to have En equal to n plus half h bar omega we are going to have. So when n equal to 0, we will have h bar omega multiplied by 1 by 2, so h bar omega by 2. When n equal to 1, 3 by 2. When n equal to 2, 5 by 2. It's equally spaced. And very important thing is, this is a ground state, correct? This is a ground state. This is a first excited state, second excited state. Now look at the operator. A dagger is here. It's a creation operator. It raises the energy from this side to that side with 1 h bar omega. Difference between these two, that will give you h bar omega. Difference between these two will be h bar omega. Difference between these two will be h bar omega. It raises 1 h bar to the excited state. Similarly, what is this A? A is the annihilation operator. It lowers the operator. So exactly it will lower with amount same h bar omega down. So this is what the graph says. We will see in detail about the graph later. However, I want to show this one because A and A dagger are rising and lowering operators. It's very important. So A dagger is a rising operator. A is a lowering operator that will rise and low with the same amount h bar omega. That's the graph. That's very important. Now, just now we said An. What is A? A is the annihilation operator, destruction operator, lowering operator. The lowering operator operates on ket n. Ket n will lower 1. So n minus 1. This will become n minus 1. Is it okay? This will lower. Suppose if it is A dagger n, this will become n plus 1. Very good. So this is n minus 1. We are going to calculate now Cn. This is the eigenvalue equation. So this is the eigenvalue equation for An. Eigenvalue equation for the annihilation operator An. Okay. But Cn we are going to calculate now Cn. Cn is a normalization constant. We are going to get the value for Cn now. Okay. Now we are going to take the bra n on both sides. Just take the bra n on both sides. Come on. This is ket n. Bra n on both sides. So that will taking the bra on both sides. So that will give you bra. That will give you bra n. Correct. A dagger. What is the dagger for this one? We are going to take the bra n. I say sir. So this will be this is an operator. So this will be Hermitian conjugate. So this will become A will become A dagger. So A will become A dagger. Is it okay? We are going to just take the bra on both sides. So that will give you bra n, A dagger A, ket n. Is it okay? On left hand side. Right hand side, Cn, take the complex conjugate. So Cn multiplied by Cn star. They are real. So Cn square. Just take n minus 1 ket n bra n minus 1. So bra n minus 1 is this one. Is it okay? So Cn square, as I said just now, Cn, that will be Cn square. Okay. So n minus 1, n minus 1. This side you have n, A dagger A. A dagger A, already we know that this is number operator. N. So number operator sandwiched between ket n and bra n. Ket n bra. What is this one? Matrix element. Very good. So it's a matrix element. See, ultimately our aim is to get the matrix element. So it's a number operator. Will you get diagonal elements? Number operator operates on ket n and bra n. Will you get diagonal elements or off diagonal elements? we will get only diagonal elements. We will get only diagonal elements because this n and this n are the same. For the same thing, we will get only diagonal elements. Very important. So n operator operates on n, will give you n with a n, with a ket n. So implying that eigenvalue equation, here you will get n bra n and ket n, that will give you 1, and bra n minus 1 ket n minus 1 will give you 1. So Cn squared will be n, so Cn will be root n. So we have found out the value for Cn. So this is root n. Is it okay? Root n. Cn equals root n. Is it okay, everyone? So n, now n is a value. Root n, we have said n is a value. Will it start from 0? Will it start from 1 or will it start from 2? Which value it will start from? Will it start from 0? Is it possible? It will start only from n. Very important concept. So it starts from 1, 2, 3, not from 0. Okay, we'll keep it in mind. Okay, so n is equal to the norm an, which cannot be negative number. So put together, that will give you a ket n, that will give you root n. Eigenvalue of a will be root n. Eigenvalue of the annihilation operator will be root n. Very important, one more question. Root n, n minus 1. Similarly, we can go for the raising operator. We will go for the raising operator. So a dagger ket n will be, we are going to calculate now the normalization constant dn with ket n plus 1. Listen to me. So now n becomes n plus 1. Come on, see here, because of this operator, a dagger operator. So this is a creator operator, correct? So it will create 1. So that's why n becomes n plus 1. N becomes n plus 1. Now again take the bra on both sides, the same procedure. Taking the bra on both sides, so this will, a dagger will become a. So this will become ket n. So ket n, a dagger n. On that side, that will give you dn squared n plus 1, n plus 1, n plus 1, n plus 1, that will give you 1. Bra on ket n plus 1. And what is this one? A dagger equal to 1 plus a dagger a. A dagger a equals n operator. So n plus 1. So this will be n and this will be n. N plus 1 operator on ket n, that will give you small n plus 1. It's a value. It's an operator. It's a value. So n plus 1, bra n and ket n. So that will be answer is 1. So your dn will be root of n plus 1. Okay. So for the eigenvalue of the creation operator will be root n plus 1. So this is given as exactly equation 2.178. So this is the eigenvalue equation of the creation operator. Okay. Thus the repeated applications of operator n, ket n, will generate infinite sequence of the eigenvectors such as n plus 1, n plus 2, n plus 3 goes on. Similarly n minus 2, n minus 1. Similarly, that also there, sequence. When you are going using the ladder up, you have to come down. No other way. This is nature. So since S is a positive integer, hence the energy spectrum of a harmonic oscillator is therefore discrete energy because it differs only by h bar omega. It's quantized. Harmonic oscillator, the energy of the harmonic oscillator is quantized. So it's a discrete measure. Thus the energy of the harmonic oscillator is given by, use this expression, that will give you En equals n plus half h bar omega. Okay. N is from 0, 1 to 3. It's very, very important. It doesn't start from 1. Number operator is 1. Okay. But here the energy value is n plus 1 by 2 h bar omega. We'll see. Don't worry, we'll see. En equals n plus half h bar omega. So starts from n equals to 0. So we'll have to give the importance for this one. This is called a 0 point energy. When you are going to apply n equal to 0, I'll say the significance of 0 point energy later, and En equals n plus half h bar. It's a very, very important relation. You just look at the old version. Planck's idea. Planck's idea is En plus nh nu, correct? Planck's idea. If n equal to 0, then En will be 0. No energy exists. If n equal to 0, there exists energy. That is old quantum theory. This is new quantum theory. After 1925, new quantum theory exists. Before 1925, old quantum theory. There n equal to 0, there will be no energy. Here n equal to 0, there exists some energy. Okay, this will not violate uncertainty principle. That's the reason. We'll see. That's the significance of 0-point energy. The lowest energy eigenvalue is given by h bar by 2. When you substitute n equal to 0, this will become h bar omega by 2, which is the 0-point energy. It is a minimum uncertainty in harmonic potential. So, as we said, this is a annihilation operator and this is a raising operator. Okay, creation operator. Now we'll go for the general solution of linear harmonic oscillator. A operator operates on psi naught, ground state. A operator operates on the ground state. What will be the answer? You just guess. Ground state is the lowest one. 0, correct? 0. A operator is a lowering operator. So it has to go one step down. The lowest one is ground state already. Already we are there in the ground state. So we can't go still. So it will be 0 again. So A operator operates on psi naught will be 0 again. So very important. We cannot go down. So 0 is the lowest one. So what is the exponential for A operator? This is nothing but this. So this is operator on psi naught. So it's a ground state. So that's why psi naught. We are going to get the general solution for the ground state as well for the excited states. So now instead of P you can write minus is cross partial d by dx. You substitute here. Okay. So this will become 0. So this equal to 0 here. This cannot be equal to 0. This term must be equal to 0 in the next term. Okay. This term cannot be equal to 0. This can be equal to 0. If it is equal to 0, we can write this equation exactly like this. Correct? 0. Okay. This is equivalent to 0. You pull left hand side this side. This term can be taken into right hand side. You will get this. So d psi naught by psi naught. I can write this. And remaining terminal you just bring it to right hand side. So you will have minus m omega by h bar x. Integrate on both sides. Integrating on both sides, that will give this. So what is the answer? So this will become log psi naught. So log e base e psi naught, which is equal to minus m omega x squared by h bar into 2 plus c. Okay. Even you can substitute for log the c value to find out the c value in terms of log. So log c. You can also do it. This is integration constant. So log c. You bring log c this side. So that will give you minus log c. Correct? So that will become log a minus log b will be log a by b. So this will become psi naught divided by, you will get c. Correct? That c is a constant. Okay. Now I am going to raise it on both sides. That is log that exponential. Basically the exponential. So that will give you log and e will get cancelled. So you will get psi naught equals that normalization constant. That c no? That c will become n1 constant. So n1 e power minus m omega by 2h cross x squared. Is it okay? Now this is the ground state wave equation. So we have found out now ground state wave function for the harmonic oscillator. If we want to find out n1, what is n1? What is n1? Normalization constant. Again we have to go with normalization condition, which is minus into plus infinity psi naught square dx equal to 1. So this becomes exactly multiplied by 2 times. So multiplied by 2 times will give you, here it is 2. Here it is, see there is no 2 here. Very important. Often you will make mistake as 2 here. Okay. This is we have square term. So you will get minus m omega by h cross x squared dx is equal to 1. And standard integral for this one will be minus and plus infinity e power minus alpha x squared dx will be root of pi alpha. Alpha is the remaining term, m omega by h cross. The standard integral. So you will get n1 squared mod n1 squared will be root of alpha by pi. n1 equal to this one. Substitute in that equation. Substitute in this equation to get the complete ground state. That will give you this. Is it okay? So this is the ground state wave function for the harmonic oscillator. We have found out. So one target, two targets are little bit over. The energy eigenvalue and the ground state wave function. We will have to find out the other wave functions also. We have found out only ground state wave function. So using which operator we have used? Annihilation or we have used only annihilation operator, and we have found out the ground state wave function. Okay, this is m omega by h bar by to the power 1 by 4 e power minus m omega by 2 h cross x square. So this is the expression for the wave function of harmonic oscillator in the ground state psi naught in the ground state. Similarly, for all the other excited states, we can find out this equation is similar to Hermite differential equation, and we can use Hermite polynomial, and we are going to use Hermite polynomial n for complete wave function. It's a general solution. Complete wave function psi n equals n hn of y e power minus y squared by 2, where y squared equal to, we have changed this expression as well. This is your Hermite polynomial. So this total expression is a general formula. Okay, and here h naught y, suppose you go for n equals to 0, so h naught y becomes 1, h naught y equals 1. You would have studied already in the Hermite polynomials. Hermite polynomial for ground state, h naught y will be 1, generating function, can you remember? So h naught y equals 1. If you substitute h naught y equal to 1, this will be exactly, you will get this. Suppose h1 will go for the first excited state, h1 of y equals 2y. You substitute here 2y and make the standard integral, get the standard integral, and you will get the expression for the first excited state. So this is for the ground, this is for the first excited state. So that will be your assignment. Okay, then another one, h3 of y, you can get it, 2y squared minus 1, 2y squared minus 1. Then another one will be h4 of y. So you can get any excited state, you can get them. Is it okay? So this is a general solution. This graph is very important graph. So just to analyze, we are going to have wave function psi, modulus of the wave function, and corresponding energy eigenvalue. For n equals to 0, n equal to 1, n equal to 2, n equal to 3. First we will go with n equal to 0. And of course this is harmonic potential. Okay. The wave function for the ground state will be e power minus x squared, that we know already. Okay, e power minus x squared. It's a parabolic potential. This first n equal to 0, it will be an even function, symmetric wave function. Symmetric wave function means on both sides this will be symmetric about its mean position, about its 0. So it's symmetry. You just look at this one, it's symmetry. Look at the wave function, it is symmetry about its 0, correct? So it's a symmetry wave function. And look at above this one, n equal to 2. This also is symmetry wave function. This also is symmetry wave function. So all n equal to 0, n equal to 2, n equal to 4, you will get symmetry wave function. The remaining things, n equal to 1, n equal to 3, n equal to 5, you will get anti-symmetry wave function. This is called odd, this is called the even. The first one is called the even function. Symmetry wave function is nothing but even function. Here, odd wave functions are anti-symmetric wave function, first one. And second one, the wave function leaks out. See, the wave function comes out, tunneling through the barrier. Very important concept. Correct? See, tunnels through. Wave function comes out of the barrier. Barrier penetration, which we studied in the last class. See? And another very important thing is, at x equal to 0 here, at x equal to 0 here, look at the point. Here the particle is found to be maximum here, at x equal to 0. At x equal to 0, the particle is found to be maximum here. Here, it is 0, minimum. Here it is negative. So that's why you have taken mod square. See, here it is maximum, here it is minimum. So minimum, maximum, it goes on changing. Particle is found to be maximum here. For all even function, it will be exactly at the center, x equal to 0. Is it okay how to analyze? Then, when you come into the energies, for n equal to 0, the energy will be h bar omega by 2. It is not here at the origin, it is somewhere here. Very important concept. So usually it starts from energy x equal to 0. It starts from here, correct? But it starts from somewhere here. That means for n equal to 0, there exists energy. That is nothing but h bar omega by 2. And here n equal to 1, you will get 3 h bar omega by 2, 5 h bar. The evenly spaced. It is quantized, discrete in energy. The energies are quantized. For all odd states, the probability of finding the particle at the center is 0. So for every energy, for every n, there will be only one energy. For n equal to 0, you have h bar omega by 2. For n equal to 1, you have 3 h bar omega by 2. For every n, you will have one particular energy. This is called a non-degenerate energy. Non-degenerate energy. So these are the energy level diagram and wave function for the first 4 states. Ground state, first excited, second excited, third for 4 states, and this is for the wave function. This is for the probability density function for the 4 states. It has been given. Any doubt? So E0 is the lowest one. Now the last section is matrix representation. So this is what very important thing. This is what our discussion goes. So he has used matrix formulation, matrix mechanics, using bracket notation, and we have solved. We have solved for A dagger, X, P, E and L. So we will discuss the matrix representation of all the parameters. The matrix element of A and A dagger can be obtained by multiplying equation. So just multiply, this is equation 2.175, this is equation this. Okay. And this equation, if you have the bra on both sides, okay, this is n, ket n, bra on both sides, you will get root n, the same thing, bra on both sides, okay, your n vector, bra on both sides. So look at this equation, you have bra n, a, ket n, right hand side will be, you have bra n prime with ket n minus 1. It says that it is not a diagonal element. It's a matrix element, okay. The answer for the matrix element will be this one. Come on, repeat. I repeat. This is a matrix element of A. This is a matrix element of which operator is this one? Annihilation operator. So this is a lowering operator. So operator of A. What is the eigenvalue? Eigenvalue is root n. And this will be your bra n dash with ket n minus 1. They are not the same. They are not diagonal elements for this matrix element. Very important conclusion. Is it okay? They must be off diagonal elements. For n minus 1, we will have to write the off diagonal elements positive, right hand side. For n plus 1, we will have to write the off diagonal elements in the left hand side. Usually this is a general consideration. So similarly you can just go with bra n prime on both sides. So bra n prime, A dagger, n will give you root n plus 1, bra n dash with ket n plus 1. Look at this one, they are not diagonal elements. If both are the same, they are diagonal elements. If both are not the same, they are not diagonal elements. So they are not diagonal elements. One is n minus 1, another one is n plus 1. So we can write this matrix as like this. What is this one? Root n. It starts from 1 to positive value. We said 1, 2, 3. So root 1, root 2, root 3. Root 1, root 2. What is this one? This one is n minus 1. Off diagonal elements. I said off diagonal elements, that side, right side. Is it okay? How to write the matrix here? Similarly, you can write for A dagger, creation operator. Okay, this root n plus 1. Okay, so you can write exactly like this. Okay, exactly like this. So A dagger will be, see n, here you have n plus 1. So not diagonal elements, this is off diagonal elements. Is it okay? Now the next matrix element we are going to calculate as X. For that what we are going to do is A and A dagger. You add A and A dagger. This is A, this is A dagger. If we add these two, this one will get cancelled, correct? And there exists, X will be there. If you subtract, X will get cancelled, P will exist, correct? This is the idea. So when you are going to add A and A dagger, you will get X component, X operator. When you subtract, you will get P operator. So now we are going to add these two. Let us see. So A dagger, take the common term out, you will get 2m omega x. Okay, multiply in the denominator, multiply divide by 2m omega. I can pull 1 2 out. I can pull 1 2m omega out. So that term will be, this term will get cancelled. We can bring this term to that side. So you will have a plus a dagger will be x divided by root of h bar 2m omega. We can bring this term, we can get the value for x. So adding a and a dagger with a constant. Okay, now you are going to, now we know already the matrix for A, we know already. Matrix for A is just now we have calculated. Matrix for A dagger, this one. You are going to add these two and get the value. Multiply and get the value for x. So add it and get the value for x. You are going to add these two and get the value for x will be this one. Multiplied by this term. So x equal to this. Very simple one. Come on, I repeat. We know already this value, matrix value. We know already the matrix of A dagger. You add these two, multiplied by this one, that will give you this. That's all. And x is a Hermitian operator. Very important concept. X is Hermitian. Hermitian means you are going to take a dagger, correct? Hermitian dagger. Take the complex conjugate, take the transpose. Rows into column, column into row. If you do it, you will get the same value. So x is a Hermitian. As I said just now, how to get the p value is subtract. You will get the p value. So when you are going to subtract these two, just to subtract, m omega x omega will cancel. You will get only p value, correct? So that will be nothing but 2ip divided by root of 2 h cross m omega. Multiply divide by 2 inside, in the denominator. You pull 1 2 out, 1 2 out. Okay, so that will give you h bar 1 2, that 2 will get cancelled. These two and these two will get cancelled, correct? So you have h bar omega by 2. Okay, cross multiplying will give you root of h bar omega by 2, correct? So you will get minus ip, which is equal to this term. Multiply on both sides by I, or multiply and divide by I will give you p equals I, this term, root of h cross m omega by 2, a dagger minus a. And of course a dagger is given by this matrix element, a is given by this matrix. You just subtract, that will give you this. Okay, very simple. Now this is a complete expression for your matrix element of momentum p. What is this Hermitian? This one also is a Hermitian operator. Take the transpose, make it into complex conjugate, that will give you Hermitian. But only thing is, if you take the complex conjugate, that will give you minus p because of this factor. In x there is no I here. In p there is an I here. Take the complex conjugate, that will give you minus p. So that's the only one thing. Otherwise x and p both are Hermitian. Both are Hermitian means we will get real eigenvalues. We will get real eigenvalues. The last section, we know that HSI equal to ESI, and we know that H equals n plus half h bar omega, and H acts on n will give you E acts on n. We know already, correct? So n on both sides, so surely it will be a diagonal element. Energy eigenvalues will be diagonal elements. Energy eigenvalues will be diagonal elements. So this is 1 by 2, 3 by 2, 5 by 2, 7 by 2, pulling h bar omega out using that expression. Finally, the number operator n. Number operator n starts from 1, 2, 3. That also the diagonal elements. See, n equals 1, 2, 3. Okay. The set of n states forms indeed a complete and orthonormal basis n space. Since the states ket n are joint orthonormal eigensets of h and n. H and n will have h and n operator and the h operator both will have simultaneous eigensets, we know already. So this will be represented infinite diagonal matrices. So this will go with infinite. So these operators are not diagonal elements. Only h and n alone will have diagonal elements. They will compute with each other. They will commute with each other. When they commute, they will have simultaneous eigenstates. So that can return as diagonal elements. But here these operators are not diagonal elements. They are off diagonal because they will not commute with n. H and n will commute with each other, and thus they have joint eigenstates. They are represented in terms of diagonal elements. And just we will compare with quantum harmonic oscillator. And this is the fact for 12 values. We are going to take n equal to 12. We will get this type of waves. Okay. Suppose we are going to take n equals 100, n equal to 1000, and we will get the dotted lines will represent the classical harmonic oscillator. So this represents the classical harmonic oscillator. This represents the quantum harmonic oscillator. When n goes very very high, n equals infinity, and this one will merge exactly with this. This is Bohr's correspondence principle. So computer simulation from using computer simulation, they have calculated for psi 1 to 12 values. I have taken from the book, from the net, for the computer simulation. Even you can use it for psi 20, psi 30. We will get exactly like this. So this is for the classical oscillator. This is for the quantum oscillator. When n goes to infinity, then both will merge each other. So Bohr's correspondence principle will be satisfied. Okay. For large number of n, quantum behavior will become into classical behavior. So this is an example. It is shown that in the figure that oscillator wave function or even function, even values of n, odd values of n. Just now we have seen. Correct? It is because e power minus alpha squared x squared. That's why it's a parabolic potential. So it is always an even function. So here the Hn of x only will decide. The Hermite polynomial will decide whether it is odd or even. So this is multiplied by this. This is a total wave function. N multiplied by Hn multiplied by e power minus alpha squared x squared is a complete and general solution. This is what we have seen. Hn is a Hermite polynomial which will decide whether it is an even function or odd function. Whereas this factor will be always even function. E power minus x, e power plus x. This is very difficult. Correct? Exponential. Here it is x squared. It will be always an even function. So this Hermite polynomial will decide whether it is odd or even. Okay. It is also noted that quantum oscillator can be found outside the parabolic potential, leaking, I said, tunneling effect. Since the wave function does not vanish at the classical turning points. It also be discussed. It implies that the particles can penetrate into the barrier to some extent. This barrier penetration is simple. It's an important feature of quantum mechanics. So the energy spectrum of the harmonic oscillator consists of equally spaced En plus 1 minus En equal to h bar omega. This exactly matches with the Planck's idea. Planck's idea is equally spaced. So about oscillating charges. So black body radiation, the energy comes out only equally spaced. Energy comes out like packets of energy, quanta of energy, bundles of energy. So there are integral multiples of h over omega. R equals E equal n h nu. Okay, n goes from 1 to 3, but here n goes from 0, 1 to 3. That's the only one difference. So as expected for bound state of one-dimensional potentials, the energy spectrum is both discrete and non-degenerate. So they are non-degenerate. So the last one, significance of 0 point energy. It's very very important one in short question. What is the significance of 0 point energy? In the case of infinite square potential, already we studied, we encounter the 0 point energy phenomena. The lowest energy eigenvalue of the oscillator is not 0. But here, En equals n plus half h bar omega. N equals 0. The answer is E0 equals h bar by 2. This energy is known as 0 point energy of the oscillator. Even at absolute 0, there will be small vibration will be there. The oscillator will have this energy even at absolute 0. This is manifestation of uncertainty principle. Suppose at E equal to 0, as in the case of say Planck's idea. Suppose if E equal to 0. If E equal to 0, the position will be 0. The momentum also will be 0. So del x will be 0, del p will be 0. This is a violation of uncertainty principle. That's the reason that at n equal to 0, E is not equal to 0. E has some value h bar omega by 2. It's a very important one. Okay. However, it can be shown that the minimum energy of an oscillator without violating uncertainty principle is h bar omega by 2. Okay, so we'll solve one problem, that is the n. It's a very simple problem, it's a very important problem. Using harmonic oscillator, we are going to use uncertainty principle to solve this one. Show that the minimum energy just now we said h over omega by 2. The minimum energy of the simple harmonic oscillator is given by h bar omega. So we are going to show that the minimum energy of the harmonic oscillator is h bar omega by 2. So we know that already del x del p greater than or equal to h bar by 2. For the simplified, just we will assume that del x is approximately equal to x. Del p equals h bar by 2 del x. Correct? Del p equals h bar divided by 2 del x. So approximately equal to h bar divided by 2x. So this can be written as 2x. And we know that E equal to P squared by 2m. So instead of P, just substitute h bar by 2x. So 1 by 2m h bar by 2x whole square plus 1 by 2 m omega squared x squared. Okay, you multiply these two and get the simplified for the energy expression E of x. So we will get this. To find out the minimum energy, we will have to differentiate with respect to x and make it into 0. So differentiate with respect to x. Whenever you differentiate with respect to x, you will get this expression. Minus h bar divided by, here it becomes x squared, 1 by x squared, x to the power minus 2 in the numerator. So that will become minus 2 x to the power minus 3. So when it comes down, x to the power 3 with a minus sign. And this side will be, you will have 2x. That 2 will get cancelled. So you will get m omega squared x equal to 0. This must be equal to 0 according to the condition, to have the minimum condition. So this term goes that side, minus will get cancelled, you will get this expression. We can get the value for x. So that is x to the power 4 equal to remaining expression. So x squared, just take the root, that will give you x squared equal to h bar divided by 2m omega. Substitute x squared here in this expression. So you will get h bar squared divided by 8m. Instead of x squared, you substitute h bar divided by 2m omega plus half m omega squared. Instead of x squared, you substitute. Similar term will cancel. Okay. For example, 8m and 2m, that will give you 4. H bar squared h, that will give you 1 h bar. So that will give you this omega, that will go to the numerator. So h bar omega by 4. Similarly, here m will cancel. This 2 and those, that will give you 4 h bar omega. Your omega squared is there. Omega will get cancelled. Your omega. So h bar omega by 4. 1 by 4 plus 1 by 4 will give you 1 by 2. So 1 by 2 h bar omega. So your energy will be h bar omega by 2. So this is the minimum energy that can be obtained using uncertainty principle. Okay. So that is the end of the class. We will stop here. Thank you, students. Bye.